Hello and welcome to Artsplainer, the video series where the sciences behind the arts are explained. Today, we'll be talking about one of the most practical applications of STEM in arts, theatrical lighting. Theater has been around since the dawn of time, but has more modernly been defined as a collaborative form of performing art that uses live performers, typically actors or actresses, to present the experience of a real or imagined event before a live audience in a specific place, often a stage. The performers may communicate this experience to the audience through a combination of gestures, speech, song, music, and dance. Elements of art, such as painted scenery and stagecraft, such as lighting, are used to enhance the physicality, presence, and immediacy of the experience. Specifically, stage lighting is the craft of lighting as it applies to the production of theater, dance, opera, and other performance arts. Several different types of stage lighting instruments are used in this discipline. In addition to basic lighting, modern stage lighting can also include special effects such as lasers and fog machines. Theater lighting employs a variety of different lighting instruments, each one with its own specific purpose and practicalities. First up, we have a PAR light, officially known as parabolic aluminized reflector light, but also referred to as a PAR can. Designed after old automobile headlights, PAR cans consist of a lamp and reflector housed inside a simple can-like housing. These are some of the most basic lights as they emit virtually unmodifiable beams of light. The beam emitted is ovular and soft with a fixed hotspot. As such, PAR cans are often used for flat lighting a large area. PAR cans are classified with a number attached to the end of a name. A PAR 64 has a lamp with 64/8 inch diameter. A PAR 32 has a lamp with 32/8 inch diameter, and so on. Next on the list of lighting instruments is a strip light, also known as a cyclorama or cyclight, border lights, or codas. These lights consist of long housing chains containing multiple lamps. Traditionally, each lamp will have its own gel color, red, green, or blue, and its own dimmer switch to allow for the mixing of any color. Cyc lights are most often used to light the background cyc curtain or the border legs to provide accents of color to a scene. Scoop lights are considered to be the most basic theatrical light as they are entirely unfocusable. These circular housings have no lenses and are often utilized due to their low cost. Because these lights emit only a large area of light, the most common use for scoop lights is in flood lighting an arena from above or for lighting backdrops. Another popular lighting fixture is called a Cornell. This fixture boasts a unique design in that its lens isn't smooth like other fixtures. Instead, the lens is ridged in a circular pattern. This hardware style allows for a wide, soft beam ideal for back, side, and top light, as well as shadows. Because Fresnels consist of a lamp with a spherical reflector inside the housing, the reflector can be adjusted and refocus the hotspot of the light. These lights are best suited for area lighting on a stage. The last conventional fixture that we will be discussing today is also the main topic of this video. ERS, or ellipsoidal reflector spotlights, fixtures are a staple for any lighting design in the modern world of theater. In fact, these fixtures are so common that they're often referred to simply by their brand name, LEGO or Source 4. Source 4 lights, as we will be referring to them, consist of a large casting unit which contains many of the internal parts of the fixture. Inside lie an ellipsoidal reflector, lamp, a dual lens system, and a shutter system. Attached to the end of this casting is an adjustable barrel with an accessory and gel frame mount. The reason these source 4s are so widely used is that the beam of light produced is widely adaptable, so the fixture can cover areas from floodlight widths all the way down to single small spots. Barrel sizes affect the throw distance and width of the light as it exits the fixture. Narrow long-distance needs are usually covered by 19 or 26 degree barrels, while short wide throws are made with 36 or 50 degree barrels. Additional accessories, like irises, can adjust the radius of a light beam, and the shutters can be used to shape the beam of light precisely to the space it is needed for. In addition to conventional fixtures that we just discussed, theatrical lighting often makes use of intelligent fixtures. These intelligent fixtures are motorized moving lights that allow the operator to control the beam output. Additionally, many of the lights can be repositioned remotely as well through the use of a motorized yoke that allows operators to adjust pan and tilt from the programming console. The ability to move these intelligent fixtures while they are lamped on allows for many of the swinging, sweeping, and circling effects that can be seen in concert lighting. Adding to the effect of movement, intelligent lights will also, oftentimes, have gobos or dichroic wheels in them, which, when selected by the operator, allows the addition of color or texture to the light beam. As a last note about fixture types, like any other technology, theatrical lighting fixtures have been evolving and improving rapidly in the past 50 years. As such, many venues are now switching to using LED-based lighting systems as opposed to the conventional systems described above. These LED lights are built the same way as conventionals, but instead of using halogen lamps, the housing cases hundreds of LED bulbs that output light in a similar fashion. The benefits to these LED-based lights is that they require much less power to operate, as the LEDs do not lose nearly as much energy to heat. This means that the producers save money on operating costs in the long run, and the electricians don't burn their hands nearly as often. Additionally, LED lights add a new type of color selection known as color mixing into lighting design. Instead of having to manually change gels or using a step motor to operate a dichroic wheel, LED fixtures can change the color of the light by varying the intensity of each of the different colored LEDs. So, when the beam is seen on stage, a blended mix of all the individual LEDs is seen, giving the illusion of one new single color. However, unlike the additive mixing of paint, where the primaries are red, blue, and yellow, meaning all the colors of the paint can be mixed from these three, color mixing in lighting design is subtractive. This means that instead of using the traditional primary colors, lighting instruments layer cyan, magenta, and yellow in varying intensities to make new colors. There are a few other terms and pieces of equipment that are important to know before we dive into our experiment for today. Most lighting fixtures are attached to a yoke and C-clamp so that they can be attached to a pipe or other surface for focusing. A yoke is the bracket that attaches to the side of the housing and provides a center point to attach the C-clamp to. A C-clamp is a cast iron or aluminum C-shaped screw-based fastener used to attach the yoke and light to a pipe. Stage pin refers to the type of electrical outlet and connector used in lighting. For a stage pin connector, all 3 prongs for the socket are in a line with one another in order: neutral, ground, and live. These connectors have 1 pole, 3 wires, and are rated for 20 amps. In addition, the flattened housing design makes stage pin the safer and more aesthetic option for theater. For this episode, we decided to conduct an experiment that would demonstrate the intensity change in different configurations for source 4 ellipsoidals and gels. To measure this, we use an instrument called a lux meter. Lux is the overall measurement of the intensity of light in a given area, or to put it simply, lux is the measure of illumination. As such, the formula for lux is lumens divided by square meters. Lux is the ideal measurement of lighting as it takes into account radiant flux and the sensitivity of the human eye in reference to the visible light spectrum, allowing for a better understanding of how bright the light actually appears to the human eye. The idea of lux comes from another older measurement of intensity that is often used in theater, known as foot candles. A candela is a fixed unit of lighting that is roughly equal to the brightness of 1 candle and equal to the value of a lumen. As such, a foot candle is equal to the brightness of 1 candle at a distance of 1 foot. ACMAS explains how a lux meter works like this. A lux meter works by using a photocell to capture light. The meter then converts this light into an electrical current. Measuring the current allows the device to calculate the lux value of light it captured. The lux light meter's calculation of illuminance is done by using the point source process. The measure of the lux light meter varies depending on the light's intensity and distance. If a point source has no reflections, a portion of the produced light reaches a surface. Compute for the square of the distance and multiply it by pi, and then by 4. The outcome must be a radius identical to the specific space from the source. This calculation is the area of the sphere at the particular distance. To measure light intensity with a lux meter, you divide the light concentration in lumens by the spherical area. The product is the illuminance in foot candles or lux, depending on whether feet or meters were used. Application of a correction factor is needed if the light reaches the surface at an angle less than 90 degrees. This can be done by multiplying the computed illuminance value by the cosine of the off-axis angle. The primary use of a lux meter is for photography, gardening, and checking health regulations. But theatrical electricians often use the lux meter to find the most intense area of the beam, or hotspot. To set up our experiment, we used the C-clamp and a sheet of MDF to attach the source 4 to one end of a 7-foot-long table. On the other end, we attached our lux meter to the end of a vertical board and lined up the sensor with the hotspot of the light. First, we recorded the resting lux reading of the room with the lights out to get a baseline reading. Then, we tested 3 different barrels, 19, 36, and 50 degree. And for each barrel, measured 14 different combinations of gel and diffusion. This gives us a total of 42 different testing parameters that we measured. In our selection of gels to use, we wanted to test a few different things. We chose gel sets that were blue, orange, and red, so that we could represent the range of the visual spectrum. Additionally, from each of these colors, we chose one saturated and one non-saturated gel, so that we could see how saturation affects the intensity of the rig. Another thing that we decided to test was the effect of diffusion on our lux meter. So we added test scenarios where diffusion gel was placed on top of each gel color test. Finally, we recorded the intensity of the lights with just diffusion and without any gel to get a control variable to compare our results against. Our baseline recording of the room reads at 0 lumens, so we know we don't have to adjust our results for ambient light in the room. As expected, our test with no gels and no diffusion yielded the brightest output for gels, and the narrowest lens was brighter overall when compared to the wider lenses. The more saturated gels dim the lights more than the less saturated colors did, and diffusion limited illumination as well. The test without gel, with orange gels, and with red gels descend in a mostly regular pattern, but the blue gels gave more varied results than the others did. The light blue allowed more light through than any other gel, but the dark blue was the most obstructive of all, with a lumen reading of only 260 in the 50-degree lens. We can calculate the transmission rates of the gel by dividing the lumen output for each gel by the lumen output of the lens without any gels added. For example, the RO2 gel had a lumen output of 15,100 and a non-gelled output of 20,200. Divide these two and you get a total transmission rate of 75%. Repeat this process for all 3 lenses and average them together to get an average transmission rate of 77%. You can see the transmission calculations in this table. As you can see from the results of our experiment, the type of gel and color you use drastically affect what the audience can see on stage. As such, it is very important that light designers and technicians take these into account when they design a show. In some scenes and shows, it may be ideal to light an actor in dark blue, but if you need the audience to make out the details on the actor's face, a different color is necessary. Designers need to understand the physics behind the lighting to understand how to best light the stage. Without STEM, this important art form would be unattainable. As always, thank you for tuning in to Artsplainer, and make sure to check out the next video where we discuss the use of Arduino and wireless technology in theater. Bye-bye.